This is a vodcast I'm making for my AP Physics B students as a way to compensate for some loss of class time that we're experiencing due to our schedule changes here. This problem is taken from Randy Knight's textbook, Physics for Scientists and Engineers. In this situation, we have a flatbed truck dumping a 50-kilogram steel file cabinet. The truck's bed is made of steel and it's slowly tilted. The questions are, what is the size of the static friction force on the cabinet when the bed is tilted to 20 degrees? And second, at what angle will the file cabinet begin to slide? I think that before you watch the rest of the video, you should stop and try the problem yourself for a while. Simply watching others solve a problem does not confer knowledge or skill to you. Sometimes you have to get your hands in the cake yourself. So to start with, instead of just reaching for some formulas, I'd like to stop and visualize the situation. We'll model the file cabinet as a particle, and we'll try to visualize the forces acting on the file cabinet. First one is the force of gravity here, which I've labeled weight. And it should be pointing straight down, but now that I have it on my screen, it looks sort of tilty. But just imagine the weight is straight down. The second force that's important is the force of friction, and that will point up the incline, parallel to the incline of the flatbed. And then the third force is the normal force, which points up and to the right. Recall that in class, when we first examined the case of the inclined plane, we found it convenient to rotate our usual xy coordinate plane so that we had an axis parallel to the inclined plane and another axis perpendicular to the inclined plane. So here, what I've done is broken out the weight force into two components, one component of which is parallel to the inclined plane, which I've labeled weight sine theta, and the other component is perpendicular to the inclined plane, which I've labeled weight cos theta. The angle theta I'm talking about is the angle formed by the weight cosine theta component and the weight force itself at the top of this picture. So once we have the components down, let's step back to our picture of our forces. The forces are in red and the components are in black. Here, what I'd like to point out is that the frictional force pointing up the incline needs to be the same length as the weight sine theta component. If friction is less, then the file cabinet will begin to accelerate down the incline. The weight cosine theta component needs to be balanced by the normal force, or else you should have an acceleration perpendicular to the incline. So now we need to see if at an angle of 20 degrees the file cabinet will slide down the incline or not. Before we do any calculating, let's go back and revisit what we know to be true about friction. Remember in class that we did an experiment using a bathroom scale, and we used it to push off a wall. We used the scale to measure both the force of friction and the normal force between our chair and the ground. So the data I showed gave us a straight line, a straight diagonal line, and we reasoned through a thought experiment that the slope of that line gave us some information about the two surfaces that we were using. So we gave a name to that slope. We called it the coefficient of friction. In this case, the coefficient of kinetic friction, symbolized as mu subscript k. So from this graph, we get a relationship. The force of friction is equal to mu sub k times the normal force. Another idea that we considered as part of our friction model was the fact that the amount of friction seems to change when you push a very heavy object. If you have that heavy object at rest and you give it only a little force, it will not accelerate. If you increase that force by a little bit, it still might not accelerate, and it will stay at rest until you reach some maximum value of force. At that point, the object will move, and you all said that in your experience with moving heavy things like couches and plasma TVs, that once you get the thing moving, it's a lot easier to keep it moving. So this gives us a notion of really two frictions that we play with in calculations. One of them is the kinetic friction, and that's given by this horizontal line on the right-hand part of the graph, and that has a value equal to mu sub k times the normal force. Then there's also this maximum possible friction before the object starts to accelerate, and we call that static friction. That is equal to another constant, mu sub s, s for static, times the normal force. So in this case, we need to find out, for the file cabinet tilted at 20 degrees, how much friction is there? And is it too much for the static friction force? At this point, I became a little bit perturbed by the fact that the problem did not tell me anything about mu sub s or mu sub k. And this small child was perturbed by the exact same fact. But don't worry, there is a clever way to solve this problem. So recall from our free body diagram that the parallel component of the weight force was pointing down the incline, but friction would be pointing up the incline. If the file cabinet is at rest, we can write this relationship, that the sum of the forces in the parallel direction is equal to weight sine theta minus the force of static friction equals 0. Then we can make a little substitution by saying that the weight is equal to the mass of the file cabinet times the gravitational field strength g. So our expression becomes sum of the forces in the parallel direction equals mg sine theta minus the force of static friction equals 0. So we're given enough in the problem so we can find out how much friction we need at an angle of 20 degrees in order to hold the file cabinet on the flatbed. We can sub in the mass of the file cabinet, which is 50 kilograms, times the gravitational field strength, 9.8 newtons per kilograms, times the sine of 20 degrees. Make sure your calculator's in degree mode. And then when we do all this math, we find the static friction we need is 168 newtons. So that value, 168 newtons, does not actually require us knowing mu sub s. We simply have to find the size of the friction force that will balance the component of weight that points down the slope. The coefficient of static friction only enters when we want to find the angle at which the file cabinet slips. Slipping occurs when the static friction reaches its maximum value, which, as we explored in class, we said was the force of static friction maximum is equal to mu sub s times the normal force. So now the question is there a way we can get at what the value for the normal force is? And the way we build that is to build the equation that describes the forces on the file cabinet in the perpendicular direction to the incline. Here, if you recall our free body diagram, we could write the normal force minus weight cosine theta is equal to 0 if the file cabinet is not accelerating. And we can sub in, like we did before, for weight to be sum of the forces in the perpendicular direction equal to the normal force minus mg cos theta equal to 0. Rearranging this, we can write mg cos theta is equal to F normal. Now if you take the equation at the top of the screen and sub it in to this one, we can write the static friction maximum force is equal to mu sub s times mg cos theta. At this point, let's bring in the equation we wrote down previously for the parallel component. Sum of the forces in the parallel direction is equal to mg sine theta minus the force of static friction equals 0 for a file cabinet at rest. We'll juxtapose this against the equation we just wrote, which was the force of static friction maximum equal to mu sub s times mg cos theta. the clever part here is that we're going to set these two equations equal to each other. And when we do that, we can write mu sub s times mg cos theta equal to mg sine theta. We'll cross out the mg on both sides, and then we'll divide sine theta by cosine theta, which, if you remember from some math class at some point, is equal to tangent of theta. So we're left with tan theta equals mu sub s, and taking the inverse of that gives us theta equal to 38.7 degrees. Now, Randy Knight, whose text I borrowed this from, suggests that we should assess this result. And he writes, steel does not slide all that well on unlubricated steel, so a fairly large angle is not surprising. The answer, therefore, seems reasonable. It is worth noting that we use the normal force is equal to mg cos theta in this example, and he says a common error is to use simply normal equal to mg, like we do on a object on a flat surface. He says be sure to evaluate the normal force within the context of each specific problem.